Hello, my good friends. Derek Deschamps here for Internetworking Influencers, your source for free Cisco certification training for network engineers. Welcome to day 10 of our free CCNA 100-105 IC&D1 training course. The Internetworking Influencers CCNA 100-105 IC&D1 training course is comprised of 13 videos, each focusing directly on a set of specific items on Cisco's official exam topic list. Today's episode will cover Item 4.1, Describe DNS Lookup Operation. Item 4.2, Troubleshoot Client Connectivity Issues involving DNS. Item 4.3, Configure and verify DHCP on a router, excluding static reservations. This includes server, relay, client, as well as TFTP, DNS, and gateway options. Item 4.4, Troubleshoot client and router-based DHCP connectivity issues. And lastly, Item 4.5, Configure and verify NTP operating in client server mode. As a reminder, today's video has a set of free practice questions that are available on our website at internetworkinginfluencers.com that will help you brush up on the topics you learned today. The questions are a true representation of the types of questions you'll face on the actual exam, so be sure to check those out once we're done. Today we are going to start things off by looking at the Domain Name System, or DNS. The Domain Name System, or DNS, is a protocol that is used to translate user-friendly host names into IP addresses. For example, DNS allows websites to be accessed using names such as www.google.com instead of IP addresses. A DNS server is used to store hostname to IP address mappings. A DNS server translates host names to IP addresses for DNS clients. A DNS client is any device that is configured to use a DNS server to translate host names to IP addresses. To show you how DNS works, let's take a look at an example. With this network, host A is configured as a DNS client. If host A wanted to communicate with file server 1, but only knew its host name, it would send a DNS query to the DNS server, requesting the IP address that is associated with the host name file server 1. The DNS server would then send a DNS response back with the IP address. The result of the DNS query would be stored in host A's local DNS cache for future use. Host A could now communicate with file server 1 using its IP address. While no special configuration is necessary to support DNS traffic on a network, there are a few DNS-related commands that you should be familiar with for the exam. To show you how these commands work, I'll begin by logging into a router that has pre-configured interfaces and going into privileged exec mode by entering the command enable. We will now go into global configuration mode by entering the command configure terminal. Now, if we want to allow the router to use DNS to translate host names to IP addresses, we can use the command IP domain lookup. We will now be able to use host names with Cisco iOS commands such as ping and traceroute. Now, to specify the IP address of the DNS server, we can use the command IP name server followed by the IP address. In this case, 192.168.0.10. And lastly, if we want to configure a static hostname to IP address mapping, we can use the command iphost followed by the hostname. In this case, router2, followed by the IP address. In this case, 10.2.2.254. The static mapping will now be used to translate the hostname router2 instead of querying the DNS server. Now, if we exit out of global configuration mode by typing exit and issue the command ping file server 1, we can see that DNS is now functioning. And if we enter the command ping router2, we can see that the DNS server was not queried, meaning our static mapping is being used. The next topic we will look at today is the Dynamic Host Configuration Protocol, or DHCP. The Dynamic Host Configuration Protocol, or DHCP, is used to automatically provide hosts IP addresses and other optional configuration parameters. DHCP eliminates the need to manually configure IP addresses on individual hosts. A DHCP server provides DHCP clients with IP addresses and other optional configuration parameters. Optional configuration parameters include default gateway, DNS server addresses, domain name, and TFTP server addresses. A DHCP client is any device that is configured to use DHCP to obtain an IP address. For example, with this network, if host A was configured to obtain an IP address using DHCP, it would broadcast out a DHCP discover message in an attempt to locate a DHCP server. The source IP address of the DHCP discover message would be set to 0.0.0.0, since the DHCP client does not yet have an IP address. The destination IP address would be set to the broadcast address 255.255.255.255. A DHCP discover message also contains a broadcast flag that, when set to 1, tells the DHCP server to communicate back using broadcasts. In this example, the broadcast flag is set to 1. Once the DHCP server receives the DHCP discover, it would broadcast back a DHCP offer to offer the DHCP client an IP address and provide other optional configuration parameters. To accept the IP address that was offered, host A would broadcast back a DHCP request. The DHCP server would then broadcast back a DHCP ACK to acknowledge that the IP address has been allocated. Once host A receives the DHCP ACK, it can begin using the IP address. A DHCP relay agent is used to forward DHCP messages between DHCP clients and DHCP servers when they are not located on the same subnet. A router can be configured as a DHCP relay agent using the IP helper address command. For example, with this network, host A and the DHCP server are not located on the same subnet. This means that if host A broadcasts out a DHCP discover message, it will not be received by the DHCP server, since routers do not forward broadcasts by default. To solve this problem, the IP helper address command can be used on the router's fast Ethernet 0/0 interface. This IP helper address command has been configured to forward any DHCP broadcast that is received on fast Ethernet 0/0 to the DHCP server 192.168.1.25. Now when host A broadcasts a DHCP discover message, the router will forward the message directly to the DHCP server on behalf of host A. The router will use the IP address of its fast Ethernet 0/0 interface as the source address, and the DHCP server's IP address as the destination. The DHCP server will then reply back with a DHCP offer directly to the router. The router will then broadcast the DHCP offer out fast Ethernet 0/0 for host A to receive. The same process will be followed for any subsequent messages. Now that we know how DHCP works, let's take a look at a few configuration examples. I'll begin by logging into a router that has pre-configured interfaces and going into privileged exec mode by entering the command enable. So let's start off by looking at how to configure a Cisco device to act as a DHCP client by configuring an interface to obtain an IP address using DHCP. To do this, we enter global configuration mode by entering the command configure terminal. We now enter interface configuration mode for the interface we want to configure by typing interface followed by the interface type and number, in this case, fast Ethernet 0/1. Now to configure the interface to obtain an IP address using DHCP, we enter the command IP address DHCP. By default, the interface will be shut down. So let's enable it by entering the command no shutdown. Now if we exit out of interface configuration mode by typing exit, and exit out of global configuration mode by typing exit again, and enter the command show IP interface brief, fast Ethernet 0/1, we can see that the interface has successfully obtained the IP address 192.168.1.1 using DHCP. So now that we've obtained an IP address, let's configure our router to act as a DHCP relay agent for DHCP broadcasts that are received on a particular interface. To do this, we enter global configuration mode by entering the command configure terminal. We now enter interface configuration mode for the interface we want to configure by typing interface followed by the interface type and number. In this case, fast Ethernet 0/0. Now to configure the interface to relay DHCP messages, we enter the command IP helper address followed by the IP address of the DHCP server. In this case, 192.168.1.25. The router will now forward any DHCP broadcast it receives on this interface to the DHCP server. Now, if we exit out of interface configuration mode by typing exit, and exit out of global configuration mode by typing exit again, and enter the command show IP interface, fast Ethernet 0/0, we can see that the IP helper address has been configured, and that any DHCP broadcast that is received on this interface will be forwarded to the DHCP server 192.168.1.25. Now lastly, let's configure our router to act as a DHCP server. To do this, we enter global configuration mode by entering the command configure terminal. Before we configure the DHCP server to assign IP addresses for a particular subnet, we need to specify which addresses we want to exclude from being assigned. To do this, we enter the command IP DHCP excluded address. Followed by the address range we want to exclude. In this case, let's exclude any address that falls in the range 192.168.0.1 to 192.168.0.30. Now, to configure the DHCP server to assign IP addresses for a particular subnet, we enter the command IP DHCP pool. Followed by the pool name. In this case, let's name our pool Subnet 1. As you may have noticed, the command prompt has changed to DHCP-config in parentheses. This means we are now in DHCP pool configuration mode. Now, to specify the subnet we want to assign IP addresses from, we enter the command network followed by the subnet ID of the subnet. In this case, 192.168.0.0, followed by the subnet mask or prefix length. In this case, let's use a prefix length of 24. Next, we'll specify the optional configuration parameters that will be provided to DHCP clients on this subnet. To specify the default gateway for this subnet, we enter the command default-router followed by its IP address, 192.168.0.1. To specify the DNS server for this subnet, we enter the command DNS server followed by its IP address, 192.168.0.10. IP addresses can be leased to DHCP clients permanently or for a specified duration. To specify the lease duration, we can enter the command lease followed by the lease duration. The default is 1 day. Let's change this to 2 days. This means a DHCP client can now use a DHCP assigned IP address from this subnet for a maximum of 2 days before renewing it with the DHCP server. To specify the DNS domain for this subnet, we use the command domain name followed by the domain name. In this case, internetworkinginfluencers.com. And lastly, to specify the TFTP server to be used by hosts on this subnet, we can use the command next server followed by its IP address, 192.168.0.30. Now, if we exit out of DHCP pool configuration mode by typing exit, and exit out of global configuration mode by typing exit again, and enter the command show IP DHCP binding, we can see that the first IP address in our pool, 192.168.0.31, has already been assigned to a DHCP client. Since the DHCP server started assigning IP addresses at 31, we know that our excluded address range is functioning fine. Now, to view information on a specific DHCP pool, we can enter the command show IP DHCP pool. Followed by the pool name, in this case, subnet 1. Here we can see the subnet that has been assigned to the pool, and that one address has been leased. To view the DHCP server statistics, we can enter the command show IP DHCP server statistics. Here we can see the number of DHCP messages that have been received. And the number of DHCP messages that have been sent. Occasionally, the DHCP server or a DHCP client may detect that a DHCP assigned IP address is already in use by another host, causing an address conflict. To view information on IP address conflicts, we can enter the command show IP DHCP conflict. Here we can see that an address conflict has been detected for the IP address 192.168.0.32. This means that the DHCP server will no longer attempt to assign this IP address. Once the address conflict has been resolved, the conflict can be cleared from the DHCP server by entering the command clear IP DHCP conflict. Followed by the IP address, in this case 192.168.0.32. Now, if we issue the command show IP DHCP conflict, we can see that the conflict has now been cleared. This means that the IP address can now be assigned by the DHCP server. The last topic we will look at today is the Network Time Protocol, or NTP. The Network Time Protocol, or NTP, is used to synchronize the time between devices. When device times are synchronized, events can be tracked more easily across devices. An NTP server provides the time to NTP clients. An NTP client synchronizes its time with an NTP server. Stratum level is used to indicate an NTP server's distance from a reference clock, such as an atomic clock or GPS. When multiple NTP servers are used, preference is given to the NTP server with the lowest stratum. For example, a Stratum 1 NTP server is directly connected to a reference clock. A Stratum 2 NTP server synchronizes its time with a Stratum 1 NTP server. A Stratum 3 NTP server synchronizes its time with a Stratum 2 NTP server, and so on. So let's take a look at an example. With this network, the external NTP server is directly connected to a reference clock, giving it a stratum of 1. Router 2 is configured as an NTP client and is configured to synchronize its time with the external NTP server. Router 2 will have a stratum of 2 since it synchronizes its time with a Stratum 1 NTP server. Router 1 is also configured as an NTP client and is configured to synchronize its time with Router 2. Router 1 will have a stratum of 3 since it synchronizes its time with a Stratum 2 NTP server. No additional commands are required on Router 2 for it to act as an NTP server. This is because any NTP client can act as an NTP server as long as its own time is synchronized with an external NTP source. However, this means that if the external NTP server was unavailable, Router 2 could not provide the time to Router 1. An NTP master clock is an NTP server that can distribute time using its local clock as a reference in the event that an external NTP source is unavailable. A router can be configured as an NTP master clock using the NTP master command. For example, with our previous network, Router 2 could be configured as an NTP master clock by using the NTP master command. This would allow Router 2 to provide the time to Router 1 even when the external NTP server is unavailable. An NTP master clock can also be configured with a specific stratum level. For example, with this network, Router 1 has been configured as an NTP master clock with a stratum of 1, while Router 2 has been configured as an NTP master clock with a stratum of 2. This means that if Router 3 was configured to use both routers as NTP servers, it would prefer to synchronize its time with Router 1 because it has a lower stratum. Now that we know how NTP works, let's take a look at how to configure it. I'll begin by logging into a router that has pre-configured interfaces and going into privileged exec mode by entering the command enable. We will now go into global configuration mode by entering the command configure terminal. Now, to configure the router as an NTP client, we can enter the command NTP server followed by the IP address of the NTP server. In this case, 198.51.100.25. Now let's configure the router as an NTP master clock so that it can still provide the time to other NTP clients if the NTP server is unavailable. To do this, we enter the command NTP master followed by the stratum level. The default is 8. Let's use a stratum of 5. Now let's exit out of global configuration mode by typing exit. So after configuring an NTP client, it is common for it to take several minutes to synchronize with an NTP server. So I'm going to edit out several minutes of waiting time before we verify our configuration. Alright, so now that we've waited several minutes for NTP to synchronize, let's verify our configuration. To do this, we enter the command show NTP associations. Here we can see that the NTP server 198.51.100.25 has been configured. We can also see that this NTP server is using 203.0.113.25 as its reference clock. The ST column indicates that this NTP server has a stratum of 2. Next, we can see an entry for the address 127.127.1.1. This has been generated by the NTP master command and indicates that the router will use its local clock to distribute time when the NTP server is unavailable. Now, if we issue the command show NTP status, we can see that the clock is synchronized with the NTP server 198.51.100.25. And that brings us to the end of day 10 of Internetworking Influencers CCNA 100-105 IC&D1 training course. Don't forget to complete the free practice questions for today's material, which can be found on our website at internetworkinginfluencers.com. The free questions will help highlight the key points that Cisco will expect you to know for the exam. Also, if you enjoy our free training and would like to show your support, please check out our Patreon page. We offer numerous perks to our supporters, ranging from additional practice questions and detailed study notes for each video, to direct access to our instructors to answer any questions you might have. I'll be back next time for day 11, where I'll cover configuring IP version 4 standard access lists and NAT. I'm Derek Deschamps for Internetworking Influencers. Thanks for watching.